So the last two sections we're going to talk about, get into some specifics on the individual BMPs. Obviously this is going to be a abbreviated view just because of being an intro, training, and limited time. So there's four different areas we're going to talk about specifically: bioretention, permeable pavement, dispersion and infiltration, and then the fourth being one that I like, newly planted and retained trees. All of which are part of the BMPs that are in the toolbox for us for low-impact development. So I'm going to talk about bioretention using predominantly decentralized vegetative facilities to both treat stormwater quality and provide flow control. The typical idea that rain gardens are a residential scale facility and bioretention is more of an engineered facility that's typical on a larger project. And then some of the stuff we're going to talk about, for the most part, shallow landscape depressions from a small contributing area. So the idea that these aren't the big stormwater ponds that we talk about, but bioretention can be a variety of facilities that can take on any number of shapes and sizes, from linear corridors along roadways to organic rain gardens in a residential setting to very structured gardens in an urban setting. So the idea, we're talking about bioretention cells, swales, thinking more in terms of linear conveyance, the concept of infiltration versus flow through. So areas where we're promoting infiltration and areas where maybe we don't have infiltration, we're next to a building, but we can still get some quality and flow control through a vegetative facility. The idea that you have the ability to get water into the facility, the idea of a pre-settling cell or sediment trap, something that provides an initial capture of sediment that's flowing from outside the facility to in. The actual ponding area, which in a swale is more of a typical V-shaped cross-section. In a planter, because you have walls, is more of a larger cross-section in that way. Bioretention soil, there's lots of discussion and research on finding the best mix of bioretention soil that meets the qualities of infiltration, water quality, and not exporting more pollution than was actually starting out. Mulch and compost, the different types of vegetation, liners for areas where we might have high groundwater or pollution, under drains for areas where we might not have total amounts of infiltration, and then how the facility is overflowing, whether it's a physical overflow that goes to another facility or whether it's overflowing into a pipe system. In this case, the distinction between a bioretention cell, something that has slope sides, typically flat bottom, it can have a lot of different shapes and sizes. If you look over on the left-hand side, we have a soil depth, we have a gravel depth underneath, and then we have freeboard, or the area on top that gives us some protection as the facility fills up and gets to the overflow. It's protection from it overflowing into the adjacent area. And then in this case, this is an infiltration facility. The other option of this is maybe a more urbanized condition, or maybe something where you have less space, is incorporating walls. Same general idea, water entering facility from adjacent pollution generating or roof surfaces, the ability to incorporate gravel layer, soil layer, and ponding water, and in this case, being able to infiltrate this into the area underneath. The other version of this is that a lot of times flow-through planters in areas where you don't have infiltration, or if you're up against a building, you don't want to put a bunch of water next to the foundation, is the ability to incorporate a liner into these facilities. So water is still coming in, it's still filling up and being treated and having detention, but instead of an infiltrating, it's just overflowing into another BMP down the line. It's more a question of specification. When you talk about a rain garden, there's not as much specificity about the design details. It's more of a residential scale. It's something that can maybe be a little bit more informal. Bioretention, you start talking about very specific details for slopes, need for under drain, and particularly the idea of, if it's officially a bioretention facility, the soil mix and how that's actually contributing to the water quality itself.
Underdrained bioretention does not provide flow control, but I think there's also ways to model it, which are going to be covered in the intermediate and the advanced training, where I think there are cases where you can. We're going to do a quick run through permeable pavement. We're going to cover the anatomy of each of the facilities in general. We're going to talk about how these permeable pavements meet the minimum requirements 2 and 5 through 7. So for erosion control, your SWIP and also your on-site flow control and treatment can all be met by pervious pavement. First type of pervious pavement we're going to look at is porous asphalt. Porous asphalt, it is a flexible pavement. It is similar to conventional. Of course, it's got less fines in the mix, so it's got about 16% voids. This particular type of pavement can be done successfully, and it can be cost neutral with traditional dense graded asphalt. However, the industry right now around placing porous asphalt successfully, I think, lags all of the other practices. So, for example, at the Stormwater Center down in Puyallup, I think it was a pretty successful installation of porous asphalt that is holding up well. I think there was also several installations around Puget Sound past few years that have not been as successful. Placement isn't done right, and if the mix design isn't using stiff enough binder, it can be problematic. But it can also be cost neutral. With dense graded asphalt, which means that if you take out your catch basins and your treatment flow control, it can be quite a bit less expensive. But with the caveat that its durability and the practicalities of installing it, we need to have our eyes wide open on that. Porous concrete, which I think is probably the more common. It's a rigid pavement. You've got a variety of porous aggregate. The one that Jason's got now is the more older school Rice Krispie version. The other two, the smaller little hockey pucks there, are what I consider my more preferred aggregate gradation, which is a much more of like a 1/4 inch. Gives, I think, consider it kind of the shopping cart friendly level of smoothness. My experience tells me that that's about as smooth as it can get and still be functional in the way that we want it to be. There's a range of aggregates. There's a range of placement methods, all of which we're going to talk about in the intermediate training in great detail. There's also a manufacturer that makes pervious pavement that uses an epoxy binder. It's clear, and you can use different aggregates for color. In terms of the unit pavers, these are a flexible pavement. They interlock just like a traditional unit paver system. Good edge restraint, making sure that it stays put. There are drainage voids provided, and then there's a dozen at least different shapes of porous pavers out there. The plastic grid system, all these sections have different thicknesses, different price points, different shapes, but they all essentially achieve the same function of containing the material. So you could basically fill these cells either with no fines kind of gravel, so you can have porous gravel if that's the look you want to have. I have a project over in Suquamish where we did the fire lane that way, and I filled the inner 12 feet as a gravel lane and the outer 4 feet on either side with grass to make it blend in. It's capable of high loads. Often with these systems, I end up putting a triaxial geogrid down in the system because geogrids are a really nice way to get some strength to the section without having to put a lot of rock under the system, and particularly if there's grass in there. It's really nice to use like a coarse sand or something that the grass can actually root in, but then have a geogrid down there to get the kind of structural capacity that you need. I know this graphic is in the manual, how it works. You can see there we've got our wearing surface of whatever type on top, and then we've got our reservoir course, which we mentioned, the gravel, open graded large chip rock over here is for storage of water and also supports the pavement, but is also as a high void content, provides storage for our pavement to infiltrate. Filter fabric is almost never used under any of these facilities, bioretention or permeable pavement, except under permeable pavement in some special cases, particularly on the sidewalls and on slopes. It's a clogging surface, that's the issue. I've used it on slopes because it's a nice mat to prevent scour if you're on a slope at that subgrade interface. That's the one place that I've used it. Or like it's saying here on the side slope to keep your fine material from the side migrating in. But for the purposes of our talk today, geotextile is a no-go unless you're in a very unique case. I wanted to discuss this idea of slopes. Picture happens to be a permeable driveway that I did at Lake Whatcom watershed, and that little detail there where I've got the flush curb. The key is permeable pavements are not under-drained. So we set the pipe down in the gravel, it's slotted on top, but it's outlet controlled. So we do allow the subgrade to flood. And I think that's an important detail, that we don't put under drains under these facilities because that tends to defeat their purposes. But we provide overflow structures so that we don't get water exfiltrating out of the pavement like on a slope. So we want to make sure that we allow there to be overflow but not under drain. Real quickly on dispersion. So this is where we are trying to take potentially piped flow and return it to sheet flow. And if our site meets the criteria for full dispersion, this can be our treatment and our flow control practice. Taking downspouts and either putting them to splash blocks and or a level spreader type facility to return the concentrated stormwater back to sheet flow. We need to be amending our soils to meet the soil quality and depth and meet our geometric limitations for the setbacks. This graphic is showing how a splash block works. There are criteria for doing that in a way that makes sure that we have usable yards. We don't want to create squishy grass yards that are not usable. So to be smart about where it's done and how it's done so that grass is usable and that we don't cause an off-site problem. But dispersion can be a pretty cost-effective and pretty effective way if our site conditions allow it. And where we can't potentially do a splash block, we can have a dispersion trench where we take one or more downspouts and pipe them into a little distribution box and then into this gravel trench which exfiltrates out and returns the piped flow back to sheet flow. Similar for a hard surface. You can see here the detail how with a rock band along the lower edge there of this driveway, and we can meet our vegetated flow path requirements. So it's all about the slope downstream and meeting the geometric setbacks to just be able to disperse water. And this is, needless to say, is about the most cost-effective kind of strategy that we can have if our site geometry allows it. And where soil conditions allow, and we've got the infiltration rate in lieu of dispersion, we can infiltrate. We can put this into a roof downspout infiltration trench here. This detail has been from the King County Manual, so this is an old idea, but still is a really important one where site conditions allow. Compost amendment. This is this BMP. A lot of information available on the web, Soils for Salmon and other places, or buildingsoil.org now, and about how we amend soil in turf areas and landscape areas to meet the BMP T513 for post-construction soil quality and depth, where we introduce organic material into the soil, which is going to absorb more stormwater runoff, require less irrigation, have more healthy plants.
So the last BMP we're going to talk about is the ability to use newly planted trees and retain trees. Obviously, that's the first option that you have, is looking at trees as a valuable resource, both from a stormwater management perspective as well as amenity, getting accurate information about the health of the tree from arborists. Valuation is an interesting concept of how much are trees worth if you factor in the time that it takes to grow them, and some large-scale significant trees. Depends on where they are, but they can get pretty hefty price tags. So the idea of using that maybe as a stick to make people aware of what the value of that is and why it's important for protection in that way. And then obviously vegetation protection as a valuable part of the erosion and sediment control. So the critical root zone is the key part, not just putting protection fencing around the trunks and calling it good. Depending on the type of tree, and this is where the arborist direction gives you some clear guidance, there are certain species where you do even up to a third or a half past the drip line of the tree. So that starts to be some significant areas, and that's looking at that as a no construction activity within that zone and being very clear that that goes into the plans. It says drip line, but that's again where, depending on the type of tree, you could have more sensitive areas for particular types of trees. But that root zone is a key part of that. That's not to say you're not able to develop within the root zone, but we need to be very careful about how we do that and how we're protecting the tree as we get into development. The feeder root zone and the broader area beyond that, totally limiting activity, but looking at specific things. This goes maybe back to where construction vehicles and staging is happening and making sure that's not happening in critical areas. Limiting trenching, and that can have implications on where utilities are routed, the type of irrigation that you're using. And then, like I said, using different techniques like tunnel boring if you do need to go through those zones itself. So the interesting part is the concept that these trees, not just being a valuable amenity that we're trying to retain and integrate, but that we're actually able to count these in your stormwater calculations. So you're looking at flow control credits for retained trees, which are a percentage of the canopy of the tree. And then in terms of newly planted trees, you get flow control credits up to a certain square footage of impervious area reduction for evergreen versus deciduous trees. The distinction being Obviously, evergreen trees are going to provide a greater amount of stormwater management because of retaining foliage year-round, where deciduous trees in our high precipitation zones are not going to have leaves. So you still get some benefit, but it's proportionally less.